This clip will examine the two different types of electrical activities that we can observe in our heart cells. So our heart cells are called cardiomyocytes, made up of cardiac muscle, but we also have what we call pacemaker cells that have the ability to generate electrical activity spontaneously, and this is how your heartbeat is initiated. And so these cells are called the pacemaker cells. So let's start with electrical activity of the pacemaker cells, and keep in mind that your heartbeat or your electrical activity that generates the heartbeat initiates at the SA node, if you remember a little bit from the electrical conduction system lesson. And so this SA node is going to fire spontaneously, so it does not need any external innervation or intervention, and it does so at regular intervals. So typically every 0.8 seconds, we have a new beat generated, and this is what gives you an average heart rate of 75 beats per minute, where the SA node will fire at 0.8 second intervals at rest. So let's begin. Let's understand how your SA node can fire spontaneously. And it's really important to note that if the SA node is not capable of generating this electrical impulse or electrical message, then we can develop another ectopic pacemaker location in the AV node or even further down the electrical conduction system. But for now, let's assume the SA node is working perfectly. So let's examine the activity of these pacemaker cells. So to begin, the first thing that we want to note is that these cells do not have a constant or a stable resting membrane potential. Instead, it starts at -60 millivolts, but as you can see, there is a drift that is upward, so an upward drift or slight depolarization, gradual depolarization that you observe. And this is due to the entry of sodium ions. So sodium inflow is resulting in this gradual depolarization right here. Now next up, let's go ahead and observe what happens at the next phase. So as you can see, I added a dotted or a dashed line here, and this is at approximately -40 millivolts. Now once this sodium inflow hits this -40 millivolt, we call this the threshold potential. And when this threshold is reached at -40, then the next thing that happens is voltage-gated calcium channels are going to open. And so this is phase number 2 of the depolarization. Okay, and so at the -40 millivolt, this is threshold. This is going to result in the opening of voltage-gated calcium channels. So I'm going to say VG, voltage-gated calcium channels. And calcium will flow in. Calcium is positively charged, so obviously this inflow of calcium is going to result in this upward deflection or depolarization. And so this is phase 2 of your pacemaker potential. Now this is going to keep going until we reach around 0 millivolts. And now at this time, at around 0, this is where we have our potassium channels start to open. So our voltage-gated potassium channels will open. And then what results is potassium outflow. So losing positive charges is going to make the cell more negative. And this is what we're going to call phase number 3, again, repolarization, since the membrane is repolarizing after being depolarized. This is going to go back on until we hit the -60, and so this is going to result in 1 heartbeat, And then the SA node is going to start with its gradual depolarization again, followed by calcium influx, followed by potassium outflux. And so this is on average every 0.8 seconds that the SA node is going to fire. So next up, let's go ahead and examine the electrical activity of the cardiomyocytes. So cardiomyocytes are going to be the cardiac muscle cells, and these are the cells that are excited by the SA node. So after the pacemaker cells generate their electrical activity, they are going to excite these cardiomyocytes, and it's the contraction of these cardiomyocytes that, or the electrical activity of these cardiomyocytes, is what results in the contraction and the ability of the heart to pump. Okay, so this electrical activity that we're going to be highlighting now in this clip is going to be what results in the heart pumping and ejecting blood out of the chamber to the next destination. So let's go ahead and look at the membrane potential of these cardiomyocytes. And we're going to start again at resting membrane potential. And in this case, in these cardiomyocytes, the resting membrane potential is pretty stable, and it depolarizes only when stimulated, unlike the pacemaker cells that we just looked at. So resting membrane potential starts at negative 90 millivolts. The first step that occurs after stimulation is going to be this depolarization observed, and this is due to the opening of voltage-gated sodium channels. So voltage-gated sodium channels open as a result of stimulation, and this is going to result in this very steep depolarization phase due to sodium influx. So depolarization due to sodium influx or inflow. Now, this is going to depolarize the membrane all the way to around positive 30 millivolts. And at this time, at this peak, this is where sodium channels are going to close. Now the next phase, right here, is what we call the plateau phase. And what takes place here is that we have the opening of slow calcium channels. So slow calcium channels will open, and this is going to result in calcium inflow into the cell. It also triggers the opening of chemically gated calcium channels on the sarcoplasmic reticulum, and the sarcoplasmic reticulum is then going to release more calcium. So the overall effect is that there is going to be an increase in calcium inside the cell, inside the cardiomyocyte. And this long plateau is really important because it's going to allow for a more sustained contraction in the heart. And this is very important because it's necessary in order to expel blood from the chambers, from the heart chambers. And then finally we have our last phase, and that's going to be number 5, this repolarization. And this is where we have repolarization due to the opening of potassium channels which results in potassium outflow. At this time, calcium channels close, and calcium is transported back out of the cell. This happens all the way until we re-establish resting membrane potential at the negative 90 millivolts. And so this electrical activity, as I mentioned at the beginning of this trace, this electrical activity in the cardiomyocyte is what will allow the cardiomyocyte to contract. And so at this time, the cardiomyocyte is contracting and then relaxing, waiting for its next trigger or excitation by the SA node.